Hi, I'm Tom, and this is Team 5's load-bearing assistive exosuit for senior design. Musculoskeletal injuries are a common type of workplace injury caused by overuse of the body when performing tasks that require repetitive lifting. These are common in warehouses, grocery stores, and other similar occupations. These injuries can not only affect a worker's job performance, but also their overall life and health. The problem is that these injuries can happen at work, but you take them home with you, and they require time out of your life to recover from. So the project goal was to create an exoskeleton designed to support the operator in their task of repeatedly lifting heavy loads. The support from the exosuit would reduce the wear and tear that the operator experiences on their body in order to promote health and wellness. And our goal is that for Senior Design 2, once we've completed the prototype, we're going to take two approaches, one including modifying the existing prototype to improve the efficiency, and a second approach to introduce a platform modularity, tailor the device to more specific fields.
Hello, my name is Xavier Manuel, and my task is to provide assistive biomechanical background for the design of the upper body exo-suit. Studying the biomechanics that govern the upper body provided guidelines for the overall frame design of the exo-suit. The provided guideline parameters included the dimensional and load requirements applied to sections of the frame, and the range of motion restrictions applied to the shoulder joint and sections of the spinal member. The applied load was modeled after an overhead dumbbell press of 50 pounds centered weight, 25 pounds applied to each arm. For the frame to provide optimal load bearing, the following was deemed required: semi-rigid spinal section of the frame, optimal frame mounting, and sagittal plane moment balance of the member applied.
Hi, my name is Enrico, Licata, and I was in charge of the Exo-Suit spine design. The criteria I was working with was to create a lightweight frame which is going to transfer load from overhead down to your core, where the wearer is going to be stronger and more stable. It attaches to the wearer through two members right here and here. This is a posture corrector and a weight belt, and these are going to increase the stability of the wearer as well as increase the mechanical advantage of the wearer when they're lifting and moving things around. The joint design is going to allow for 60-degree movement forward, and it's going to prevent movement from side to side and backwards. And this is because if you're lifting something heavy overhead, we don't want any unnatural torques to be placed on the body. Finally, we have the compression member, which is located at the bottom of the spine. This was inspired by a human vertebrae to compress as a load is applied to the spine. The reason we want this is it should feel more natural to the wearer. We don't want just a stiff rod attached to their back. We're going to test out the spring constants empirically by actually wearing the prototype when we develop it and see which compressions feel more natural. I mean, if it doesn't compress at all, it's not going to feel good, and if it compresses really fast, it's also not going to feel good. So that's something we're going to move forward and work with.
This is Kevin. I'm the extremity designer of load-bearing exosuit project. The goal for me is to design a lightweight and flexible exosuit arm that shifts the amount of weight of the load from user's arm to their body, which is attached to the frame or on the torso. Basic requirements of the design are the ability to lift about 50 pounds of weight. The design should be adaptable to different body shapes, and it should be lightweight and should be complex to wear. Arm design will have a backplate that connects to the torso frame. It will also have a sole plate that goes over the shoulder, and the servo motor will be mounted on top of it. Other end of the sole plate is connected to the joint, and the joint will have about 120-degree rotation on sagittal plane. Joint will have an extension to bicep, and it will be mounted on arm braces, which will wrap around the biceps. This is a dimension drawing of the design.
To supply energy to the system, a removable 24-volt battery pack will be used. This is what will power the two electric high-torque servo motors, which will drive the shoulders. The system will be controlled with a glove that has a flex sensor and an on-off button. A flex sensor is mounted to the index finger to find how much the index finger flexed to determine how much power to send through the system. For this project, an Arduino Uno is used to help control and regulate the system. This uses the flex sensor as a variable resistor, which is able to determine how much bend and how much power is needed to be applied. Uses this as a kill switch just in case to deactivate the power if it's not desired at that exact moment. The system is able to output the resistance, the bend angle, and the amount of power desired, and from there it's able to determine what kind of pulse signal needs to be sent to the rest of the system to help power the arms.